Sorry, I forgot to record. So, all right. So I can consider LP to be a subvector space of LP prime star. So this subvector space is a closed set. Why? Because LP is complete in the sense that if you have UN, which is a Cauchy sequence in LP, then this sequence has a limit, and this limit is also in LP, right? Meaning that, okay, LP is closed. In other words, LP is a closed vector space of LP prime star, right? So from this, can I say that LP is reflexive? Yes, so Stephen got it correctly. Why? Because we know that, okay, if M is a closed vector space of a space E, which is reflexive, then M has to be reflexive. Right? In this case, LP is a closed vector space of LP prime star. All right. So which means that LP has to be also reflexive. Right. So Stephen, so yes. So Stephen got it correctly, right? So LP prime is reflexive, which means that the dual of LP prime is also reflexive, but LP is closed, a closed subspace of LP prime star. So then LP is also reflexive, right? So the answer of Stephen is correct. So which means that for P is smaller than 1 and bigger than 1 and smaller than 2, LP is also reflexive. And we, so therefore, LP is reflexive for P, which is smaller than infinity and bigger than 1, right? And we finished this proof. So the proof of this is complicated, right? But it's worth that you see it once, so that when you need it, you can come back to the proof and then review everything. Any questions on this? All right, so if there's no questions, let us move to the Ries theorem, because the Ries theorem will be an extension of this proof, right? So the Ries theorem. The Ries representation theorem, right? So suppose that P is going from 1 to infinity, and suppose that phi is in LP star, right? LP prime star. Then there is a unique function u in LP such that phi of f will be the integral of u dx for f in LP, right? Right. So this is basically the Ries representation theorem. So in the previous proof, what we did is the following. We associate all of the u, right, with a tu. So the u is in LP and the tu is in LP prime star, right? So in other words, this is LP and this is LP prime star. And so you're gonna map U to TU. And then you can consider LP to be a subset of LP prime star, right? So in the previous proof, what we show is that, okay, LP is a closed vector space, subvector space of LP prime star. But here, what we show is that LP is indeed the same with LP prime star, which means that the thing outside will be empty. All right, so I explain again. So this theorem says that, okay, if you pick a phi, which is a member of this LP prime star, right? Then there has to be a U in LP so that this linear map phi of f can be written in the form of the integral on RD of U times f dx for all of the x for all of the f in LP prime. So LP prime, right? So this is in some sense the reverse of the previous fact that we just covered. In the previous proof, what we show is that, okay, if I pick a U in LP, then I can define a TU in LP prime star, right? So so TU will be integral of U times F for all of the F in LP prime, right? Now, so I define TU of this way, so then I can map anything from LP to this TU, which is a function in LP, which is a member of LP prime star. All right, and we concluded that LP is a closed subspace of LP prime star. But in this case, we also, so in this theorem, we prove the reverse. The reverse says that, okay, if you pick any phi, then you can also find a U here, such that this TU has to be the same with this phi. All right. So basically, what we want to say here is that LP is the same with LP prime star, which is the risk representation theorem. Any questions? It's good. All right. So now, so here you have this U and here you have this TU, right? So you map it here. And then this is LP prime star, this is LP. All right. So we consider LP to be a subset of LP prime star. So I can draw another picture of this type. So this is LP, right? And this is LP prime star. So in the previous proof, we showed that LP is a closed subvector space of LP prime star, right? And now we have to show that for the exterior, there's nothing, right? Right. So the main idea of this is quite tricky. So this is a very surprising idea, a very nice idea. All right. So the ideas would be the following. So you this set A, and this is the vector space B, right? So we consider two vectors. Consider two norm vector space. A and B, right? They have the same norm. So A is a subset of B, and then they also have the same norm. A is a subset of B, and they are Banach space, right? Now, So if I consider if for of the L, which is in B star L of F to be 0 for F in A, then L is 0. Then this implies the fact that B and A has to be identically the same, right? So this is, of course, this is one of the trick which is not trivial, and this is a very beautiful trick that we have to learn, right? So the idea is the following: you consider two spaces A and B, they're both non-vector space. Now, if this thing happen, if this whole thing happen, this whole thing is the following: you pick any continuous linear vector space, continuous linear mapping on B star, right? If this linear mapping on B star is going to be 0 for all of the F in A, right? So if L of F is 0 for F in A, then L has to be 0. Then B has to be the same with A, right? So someone understand why this happens, right? So this is a vector space B. This is the vector space A, right? Now we consider a linear map on the full space B. Suppose that this linear map is 0 for all of the F in A. Then this linear map has to be 0. So if this happens, then B has to be the same with A. Okay, can you understand why? Can you explain why? So the hint is the following. The hint. So suppose that B is not the same with A, right? Which means that I can pick a vector V in B and not in A. So I have the V here. All right? It's good. All right. So now, so suppose that B is a subset of R2, for instance. Right? Say it's RD. Suppose that B is a subset of RD, right? Special case. Right? Suppose that B is a vector space, but this is finite, right? So B and A are finite. All right. So because B, so I define a linear map which is of the following type. So I define L of this say I'm gonna move to this space, right? I explain again. So I have this space A and I have this space B, right? And I have this V which is outside of B and A, right? So B and A are finite dimension. All right. So can we construct a linear map on B, so a linear map L on B such that L of any vector U will be 0 for U in A, but L of V is not 0, right? So I simplify my questions. Now I have two vector space A and B, right? They're both finite. My question is that, okay, so I suppose that B is not the same with A, which means that I can choose a V which is outside of A but inside of B. Can I construct a linear map on the full space so that I pick any U in A? This linear map return to 0, but this linear map on V is going to be different from 0. Is it clear? The question is clear? Say, for instance, okay, so I simplify these questions. Yes, okay. So I'm gonna simplify these questions a little bit more. Simplify question. Suppose that I have a vector space A, which is of U1, UN, right? So those are the basis of this vector space, right? So now the space B will be U1, U2, UN plus 1, right? So so U1, UN are basis of A, and U1, UN plus 1, the basis of B, right? So suppose that I have a vector space, which is the expansion of the basis U1, U2, UN, right? And now suppose that I have the vector B, which has the basis U1, U2, UN, UN plus 1, right? So can I construct a linear map L such that L of U will be 0 for all of the U in A, and L of U and plus 1 is different from 0, right? So of course UN plus 1 is not in A, right? UN plus 1 is not in A. So I think this is a very simple question. I have a space which is n dimension, right? So A is the expansion of the basis U1, U2, UN. Okay, B is the expansion of the basis U1, UN, UN plus 1, right? So which means that this UN plus 1 is the vector which is in B, but not in A, right? UN plus 1 is in B, but not in A, right? So can you construct a linear map L such that L of U is 0 for all of U in A, but L of UN plus 1 is different from 0?
Would it just be like the function getting the projection onto the n plus 1?
Yes, excellent. So Jonathan did it correctly, right? So basically so for Jonathan, the idea is the following. So if you pick a W in B, right? So W will be alpha 1 U1 plus alpha n plus 1 UN plus 1. All right. So now I'm gonna consider a linear map which is of the type n plus 1. So I project this vector onto the last component, all right? And I take the last coefficient, right? So alpha 1, alpha 2, alpha n plus 1, they are all real number, right? So which means that this is a linear map which is continuous, of course, because this is bounded. And then L of U is going to be 0 for all of the U in A, and L of UN plus 1 is going to be different from 0, right? It's clear? Right? So if you consider a linear mapping, which is of course continuous, because this is bounded, so this linear mapping is the projection on the last component of this of the n plus 1 coordinate, right? So then this linear mapping will satisfy the condition that L of U is 0 for all of the U in A, but L of U plus 1 is different from 0. All right. So in other words, all right. So if A is a subspace of B, A and B are two vector space, vector norm space. All right. And A is a subset of B. So if I can, if there is for all of the L, such that L of U is going to be 0 for all of the U in A, imply that L has to be 0, then I has to be the same with B, right? You see the points? So in B prime, because suppose that A is different from B, then there is this UN plus 1, right? And then you can construct the L to be the projection onto this vector component, right? So this L of W, so this L of U will be 0 for all the U in A, but L is different from 0, right? It's clear? Questions? It's good, right? So explain again, which is so this is a little bit abstract result, right? So suppose that I have two vector A and B, right? Suppose that B is bigger than A in the sense that you can find this vector UN plus 1, which is not in A but in B, but it belongs to B, right? So then you can construct a linear map, which is the projection onto this vector. And this projection is a linear and continuous map, right? This projection satisfies the condition that it has to be 0 for all of U in A, because you project only on the last component, right? So you project only on this component, but it is different from 0 at this last component, right? So which implies that, okay, if you can show that, okay, for all of the linear map on B star, the L of U is 0 for all of U in A, implies that U has to be 0, then A has to be the same with B. Otherwise, there is this last component, so that you can construct this linear mapping by projecting onto this last component, and this satisfies the fact that it is 0 for all of the U in A, but it is not a 0 linear map. Questions? It's clear? So this is what we are going to do, right? So in this case, we're gonna apply this strategy. So in this case, we have that LP is a closed subspace, vector space of LP prime star. So this is my A, and this is my B. I want to show that A is the same with B. All right. So what I'm gonna do is I'm gonna pick an edge in LP prime star, which is B star, right? Say not H, say L, right? So according to the strategy that the idea that I just showed you previously, we know that this L is a closed subspace of LP prime star, right? And we want to show that A and B they're the same. So what should we do? We're gonna pick an L, which is a linear and continuous mapping on LP, LP prime star, which is B star, right? So, and we will show that if L of U is 0 for all of the U in A, then L has to be identically 0 right? So we show that, okay, we show that L of U is going to be 0 for all of the U in A. So if this happens, if L of U is 0 for all of the U in A, then L has to be identically to 0. So this is what we are going to show. And if this happens, then the consequence will be A and B, they are the same, right? It's clear? So the idea will be to show that for all linear mapping on continuous linear mapping on B, L of U, if L of U is 0 for all of the U in A, then L has to be 0, all right? Then if this happens, then by the previous idea, A and B has to be the same, right? So we're gonna show this on Friday. But basically, this is Rich's idea. So this is striking idea and very beautiful idea, and this is not trivial to recognize this strategy. That's good. Any questions? So if there's no questions, we're gonna continue on Friday. All right. Thank you. Have a nice afternoon.
Thank you.
Thank you. Bye.
Thank you.
Thank you.
Thank you.
Thank you.